the last class I had introduced the cosmological metric, which I have written over here, and I had explained to you the various terms that occur in this. So, this is the line element for the cosmological metric. T is the cosmological time, r, theta and phi are dimensionless comoving coordinates, they are dimensionless. We have a constant k which can take values -1, 0 or +1. This decides, so okay, so this part of the metric refers to space and this part to time. The value of k decides the curvature of space. If k is -1, we have a negatively curved space, a space of negative constant negative curvature. If I have k equal to 0, we have a flat space with no curvature. In both these cases, r can vary from 0 to infinity, the space is infinitely large. And then we have the situation where k is +1, we had discussed this in some detail in the last class. This is a space with positive curvature, it is a 3-dimensional sphere S3. In this space, the value of r, for obvious reasons, you can see here we have 1 minus r square in the denominator. The value of r is restricted in the range 0 to 1. So, this is a compact space, this space has a finite volume, it does not have an infinite volume, it does not extend to infinity, it is a 3-dimensional sphere. So, I have explained this part, I have at least explained all the terms in this part. This L is a length scale which decides the curvature, and it is important only when k is +1 or -1. When k is 0, I can absorb it inside here, and L when k is +1 or -1, L has a value given here. It is decided by the Hubble length c by h naught and 1 by square root of the omega curvature naught, present value of omega curvature. A is the scale factor, which again is dimensionless. Now, let us continue with this discussion of this line element today. Now, let us ask the question first that there are 2 points. So, we have in this is the space which has these coordinates r, theta and phi. On this space, I have 2 neighboring points with different coordinates, and the question is, what is the comoving distance between these 2 points? So, the 2 different points will have different values of r, theta and phi, and the difference is dr, d theta, d phi. So, the comoving length dl, the comoving distance between these 2 points dl square is L square. So, you can identify which part. So, this part is the spatial, this tells you the length, the distances, this tells you the time interval. This total together you get the interval, this tells you the times elapsed, this tells you the distance separation. So, if I take out the scale factor, the remaining thing is the comoving distance. So, this is L square d square r by 1 minus k r square plus r square d square theta plus sin square theta d square d phi square. So, this will give us dl square is the comoving distance between those 2 points dl square. So, I can calculate if I have 2 points which are at a finite separation, not at an infinitesimal separation. I have 2 points, let us say this and this. I want to calculate the comoving distance between them. The comoving distance L is going to be the integral. So, I have to, what I have to do is I have to integrate this, the square root of this. So, I have to integrate the square root of this. So, d r square 1 minus k r square plus r square, and this we can call, instead of repeating it every time, it takes time to write, we can call it d omega square. So, plus r square, this is the distance, the separation in angle. So, we have to integrate the square root of, to integrate this between these 2 points. Okay. Usually the curve will be parametrized by giving r, theta and phi in terms of some parameter lambda. So, I can just convert this into a single one dimensional integral. Okay. So, this gives me the comoving distance between 2 points at an arbitrary separation. Now, the next question is, what is the proper distance? Now, I have told you already that you could send a light pulse. So, again let us consider and I have 2 infinitesimally very close by points. I could send a light pulse from here to here and then this and bounce it back from here. So, this observer here will again send back a light pulse to this, and if we assume that the light pulse can propagate this distance on a time scale which is much faster than what that the rate at which A is growing, so that we can assume A to be a constant, the time that the light pulse takes to cross this, that is going to give us the proper distance c into delta t. So, the proper distance is the value of the scale factor, that time c into delta t, you can check here. So, it is quite straightforward, c into delta t. For light, ds square is 0, light travels along null curves, null geodesic. So, for light ds square is 0. So, c dt is equal to this whole thing over here. So, the proper distance, which is this c dt, that is how you get the proper distance, multiply the time light takes to propagate with the speed of light, is essentially the scale factor into the comoving distance. So, this is going to be A into dl. And if I had 2 far away separated points, points at a finite separation, the proper distance would be A into L, where L has to be evaluated by doing that integral which I had written down. Now, if you ask the question, let us ask the question, how would you conceptually measure this proper distance? If I were to send a light pulse from here to here, it could take a large time, and during that time interval the universe would expand. So, the scale factor would change. So, you could not measure this proper distance by sending a single light pulse from here to here and then sending it back, no. So, what conceptually what you have to imagine is that there are several observers located along this who can each send a light pulse from here to here. This observer can send at the same time send a light pulse from here to here. So, by measuring these small proper distances, you can combine the information and get the total proper distance. Okay. This is how we can conceptually think, visualize how the proper distance can be measured. In reality, it cannot be, not feasible to implement this. So, this is the proper distance. So, we have discussed two distances which you can define, which I have defined, and how you can, I have discussed how you can calculate them using this line element. Now, third, more important, let us now study the propagation of light in this space time. None of these distances, the comoving distance or the proper distance, can be directly measured. Okay. So, directly measured things are all measured through the propagation of light. It is not feasible to send a light signal to a distant galaxy and then reflect it back from there. So, there are other methods in which distances are measured in on cosmological scales. So, we have to discuss those, and to discuss those, first we discuss the propagation of light. So, the line element I can write in short. So, light propagation. Light propagates along null geodesics, along null trajectories where the interval is null, 0, right, because light travels at the same at the fixed speed c, we know this, the interval has been defined like that. Now, the line element ds square can be written as c square dt square minus a square dl square, where dl is the comoving distance between the 2 points, and for light this is 0. Now, in the usual space, light, the speed of light is a constant. It covers in the Cartesian coordinate, it will cover the same amount of coordinate in 1 second at every instant of time. But here this a of t is a increasing function of time, is a time varying function. As a consequence, in the 1 second, light will not cover the same, the amount of comoving distance that light covers will depend on the value of a. I suppose I fix dt to be 1 second, then the delta L, the comoving distance that light covers, will depend on the value of the scale factor. If the scale factor is large, it will cover a small delta L. If the scale factor is small, in 1 second it will cover a large delta L, because the physical separation is a delta L, that is what is unchanged. Okay. So, it is a little, this introduces a little complication if you want to study the propagation of light, and it is convenient to introduce something called conformal time, very useful in cosmology. So, for studying the propagation of light in cosmology, it is useful to introduce the conformal time, which is defined like this. So, this line element ds square can be written by taking the scale factor common. So, if I take the scale factor common, I have a square c square dt square by a square minus dl square. So, I have taken the scale factor as a conformal, this is called a conformal factor. A factor which multiplies the overall line element can be thought of as a conformal factor. This kind of a factor is a conformal factor, and we can write this as a square c square d eta square minus dl square, and this eta is the conformal time. So, d eta is defined, let me put the definition here, d eta is dt by the scale factor at. This is how the conformal time is defined, right. So, we have taken the scale factor outside, and this. Now, this is how the line element is written in terms of the conformal time. Now, if you want to study the propagation of light, light travels along delta ds square is 0. So, along the propagation of light, you have c d eta is equal to dl, d square is 0. So, c d eta is equal to dl. This is the propagation of light. So, if you use conformal time, in a unit conformal time, the distance covered by light, the comoving distance covered by light is essentially c, okay, even if the universe is expanding. So, in conformal time and comoving coordinate, the speed of light is c, okay, otherwise the speed of light is not c if I am working in the usual cosmological time. If I use conformal time and comoving coordinate, the speed of light is c. In this coordinate system, I get c as the coordinate speed at which light is moving. Okay. Now, this is very convenient. For example, let me draw a space-time diagram. So, if I draw a space-time diagram, instead in terms of L and c eta, observers at fixed comoving coordinates will move along straight lines in this space-time diagram. Their distances do not change. So, this is one observer at a fixed comoving coordinate at the origin of the coordinate system. This is another observer at a fixed comoving coordinate. Its time, conformal time, just evolves. This is another one. And if we choose the origin of the conformal time so that Big Bang occurs at eta equal to 0, if we can choose this, then this is where the Big Bang occurred. So, it is meaningless to talk of anything before this. This is all ruled out. The Big Bang occurred over here, the universe started from here, eta equal to 0. Okay, so, we can, in many situations we can choose eta so that eta equal to 0 corresponds to the Big Bang. So, this is where the universe started from. So, it is meaningless to talk of events before this. Okay. And in this diagram, suppose a distant galaxy emits a light photon and we are receiving it now. So, in this diagram that will be like this. This is the light emitted from the galaxy. It will travel at 45 degrees and reach the observer here. Okay, this is a straight line at 45 degrees. So, this conformal time is very convenient for studying the propagation of light and for various other things also in cosmology. Okay. If you work in terms of the conformal time and the comoving coordinate, light propagates at 45 degrees. Now, having given this background, let us start calculating. The first thing that we shall calculate is as follows. We shall calculate the redshift of light as it propagates in this universe. Okay. So, the situation that we are considering is as follows. Let me explain this. There is an observer sitting, let us say at the origin. And there is a galaxy G located somewhere over here. Now, the galaxy G emits light and the light is received by the observer. That is the situation, and we would like to know if there is a frequency shift or a wavelength shift in the light as it propagates from the galaxy to the observer. We would like to calculate that. Okay. How do we calculate this? So, the method to calculate this, let me start the calculation. So, we know that light will propagate along this, where along an interval where along a separation where along trajectory for which the interval is 0, okay. Or we can say that light will propagate along this trajectory of light c dt is equal to a dl, right. The dl is the co-moving distance between from here to here, or dl c dt by a is equal to dl. And there could be a plus or minus sign relating these two. Okay. And if I want to calculate the total time, the okay, so if I can if I integrate this dl from the position of the galaxy to here 0, okay, from 0 to L, this should be equal to T emitted and T observed, right, because light is travelling along this. So, it starts from co-moving position 0, this separation 0, it travels all the way to L. So, light was emitted at T emitted, it is being observed here at T observed, okay. So, light was emitted at T emitted, it is being observed here at T observed. Now, we want to calculate if there is a change in the frequency of the light or the wavelength of the light as it propagates. So, for this purpose, for the purpose of this calculation, we think of light as a wave. So, light at the emitter is a wave, so this wave has certain crests, and the separation between these crests determines the frequency. The inverse of that gives the frequency, right. So, let us say that this is emitted at T emitted and this is emitted at T emitted plus delta T emitted, okay. Now, a similar wave train will be observed by the observer, and this will be, the first one will be observed at T observed, the second one will be observed at a later time T observed plus delta T observed, okay. And we know that the integral on the right hand side gives us just the co-moving distance between these two L, right. So, we know that the integral T emitted to T observed dt at corresponding to the emission and absorption of the first crest, this is equal to L. Now, the second crest also has to cover exactly the same co-moving distance. We are assuming that the galaxy and the observer are sitting at fixed co-moving coordinates, they are expanding with the universe. So, they are sitting at fixed co-moving coordinates. So, the co-moving distance between them does not change. So, this is also equal to T emitted plus delta T emitted T observed plus delta T observed dt by at, right. The co-moving distance between them does not change. So, for the first crest this holds, for the second crest this holds. The second crest was emitted at T emitted plus delta T emitted, it was observed at T observed plus delta T observed. Now, the second integral this can be written as 3 integrals. The first integral is from T emitted plus delta T emitted to T emitted. Okay, so I am writing it as 3 integrals. The first integral is T emitted plus delta T emitted to T emitted. The second integral is T emitted to T observed, and the third integral is from T observed to T observed plus delta T observed of the same quantity dt by at. Right, I have just broken up this entire time interval into 3 parts. First is from here to here, then from here to here, and then from here to here. Okay. I hope this is clear. Now, since this is equal to this, we see that this term exactly cancels out with the second integral, and we are led to the conclusion that T emitted plus delta T emitted dt by at. So, we are led to the conclusion that this integral plus this integral should be equal to 0, because this cancels out with this. So, this integral plus this integral should be equal to 0, or you can say that this is equal to minus T observed plus delta T observed dt by at. Now, this delta T observed and delta T emitted are extremely small, infinitesimals. So, for infinitesimals, this integral can be replaced by the value of at into this. Okay. So, assuming that this delta T is very small, delta T observed and delta T emitted, emitted and observed are both small, one of them should be emitted, sorry, this should be emitted, right. This is all emitted, this is all observed. So, assuming that this delta T's are very small, we can write this as the left hand side, we can write as delta T emitted by at emitted, and there will be a minus sign because it occurs at the lower end. So, minus is equal to minus delta T observed by at observed. Okay. So, I am assuming that this is extremely small, so that you can assume this at does not change over that interval, and you can write it like this. So, finally, you are led to this fact that the wave, the light wave, the crests are emitted at an interval delta T emitted, they arrive at the observer over here at an interval delta T observed. These two are not the same. That is the final conclusion that you are led to. These two are not the same. Delta T observed by delta T emitted is equal to at observed by at emitted, right. So, this gets scaled by exactly the amount by which the scale of the universe expands. Okay, this gets scaled by exactly the amount by which the universe expands, and we know that this delta T delta t observed and delta t emitted, they are inversely related to the frequency of the emitted light and the observed light. So, you can say that the ratio of the observed frequency, the emitted frequency to the observed frequency is the inverse of the ratio of the scale factors, and this is the ratio of the observed wavelength to the emitted wavelength. Okay. So, from this we can find out, we can calculate the shift, how much does the wavelength change, okay. And we find that the wavelength gets scaled. So, light is emitted at a particular wavelength when the scale factor has some value. If the scale factor becomes doubled, the wavelength also gets doubled. So, if by the time the light reaches the observer, if the universe has doubled in size, the wavelength also gets doubled. So, the wavelengths get stretched by exactly the same factor by which the universe expands. Okay. This is the phenomena of redshift. So, in this relativistic interpretation, the phenomena of redshift is closely related to the expansion of the universe. The wavelength gets scaled by exactly the same factor by which the universe expands. That is the bottom line. Okay. And how had we defined the redshift? So, the redshift Z or the way in which we had defined the redshift was 1 plus Z into lambda emitted is the observed wavelength, right. 1 plus Z is the redshift into the emitted wavelength is the observed wavelength. That is how the redshift is defined. So, from here we see that the redshift is related to the scale factor. How is the redshift related to the scale factor? It is the value of the scale factor when the light is observed divided by the value when the light is emitted minus 1. Okay. So, this is how the redshift is to be calculated in an expanding universe. The redshift, this is how the redshift is related to the expansion of the universe. Okay. So, let me now ask you a question. There are two things which follow from here. It is obvious that you are going to have a redshift positive Z if the universe is expanding. If the universe is contracting, on the contrary, if the universe is contracting, the scale factor is going to be smaller when the light is observed. So, this number is going to be negative. Okay. So, this is very obvious. Now, let me ask you a very simple problem. So, this formula is very easy to apply. So, let me ask you a very simple problem. We see a galaxy at a redshift Z equal to 3. What at present? So, I am sitting at present and I observe a galaxy at redshift equal to 3. What was the value of the, so we assume that the scale factor at present is 1, that is what we have been doing throughout, right. We have assumed that the value of the scale factor at present is 1. If the observer is there at some other time, then you have to use this formula. At present scale factor is 1. What was the value of the scale factor when the light was emitted? So, the value of the scale factor when the light was emitted, A emitted, is 1/4. Okay, that is straightforward to evaluate from here. So, the universe was 4 times smaller when the light was emitted from the galaxy. Okay. So, now we know we have a clear picture of what this redshift is about. Okay. Earlier our discussion of the redshift was based on Doppler shifts, which exactly matches for this with small values of Z. We can see later that interpretation exactly matches with this for only small values of Z. The Doppler shift interpretation, you have difficulties when you approach the speed of light, unity, or redshifts of order unity. Okay, this is the correct picture from the full relativistic analysis, this is the correct picture that we have arrived at, okay, and this is valid at all values of z. The next question that we shall address is what is the relation between redshift and the coordinate distance. So, we would like to calculate the relation between z and the redshift and the coordinate distance and the coordinate r, okay, that is the coordinate distance. So, let me first define what the problem is. Again, the same picture, there is an observer over here and there is a galaxy G. The observer is receiving light from this galaxy and the light appears to this observer at a redshift z. So, the observer now asks the question, how far away is the galaxy from me? What is the distance to this galaxy? Now, in this cosmological metric, we have already encountered two kinds of distances, the proper distance and the co-moving distance, right. To calculate both of these, you need to know essentially the value of r, because this here we have chosen the origin, so that the observer is here, the galaxy is in the radial direction. So, we would like to know the value of r corresponding to this galaxy. Once you know that, you can determine both co-moving distance and the proper distance. Okay. So, that is the question that we are addressing. So, if I know the redshift z, how can I calculate the value of r? Okay. That is the question that we are addressing. Another question that one could also address is what is the time at which the light was emitted. I know the present age of the universe, I have measured the redshift of the galaxy from where the light is coming. What is the time when the light was emitted? How back in the past was the light emitted? Okay, that is another question we could ask. So, let us take up this question, these questions. So, the first thing that we shall do is that we shall calculate what is the conformal time corresponding to this value of redshift, okay, because we know that the light is propagating along the radial direction. Along the radial direction, ds square we know is 0 for light, and light is propagating along the radial direction. So, we do not have this, okay. And the question that we are asking is what is the conformal time, okay. So, along this null geodesic, let me put the problem this way. Along the null geodesic, C dt by AT, T emitted, T observed is equal to d eta, eta emitted, eta observed, C d eta, that is how d eta has been defined, and this is equal to L 0 to r dr square root of 1 minus k r square, right. That along the light's path, ds square is 0. So, this term should be equal to this term, which is what I have written over here. C dt by A should be equal to dr by into L by 1 minus square root of k r square, and this is also equal to C d eta. Now, we would like to determine all of these things in terms of, we know T observed we know eta observed, etc. We want to determine all of these things in terms of redshifts, in terms of the redshift. Okay. So, to do that, the first thing that you have to do is that you have to write this in terms of the scale factor, right. Once you know the scale factor, you can determine the redshift, right. So, we use, what we do is we write this dt by A as dA. So, we want to write dt by A in terms of dA. A is the scale factor, right. So, what is the, how would you write this? We know that dA by dt is, let me, okay, we know that h t is 1 by A dA dt, we know this, right. So, using this, what we can do is we can write dt as equal to dA by A into h, okay. Or this we can write as this. Fine. So, this allows us to write this term as C the integral dA by A square. Now, the Hubble parameter is typically known as a function of the scale factor, right. So, we can write this as H A. The limits of the integral t observed, the value of the scale factor at t observed, if it is at present, if the observer is at present, the value of the scale factor at t observed is 1, and the value of the scale factor at the time when the light was emitted can be written in terms of the redshift. So, the value of the scale factor at the time when the light was emitted can be written in terms of the redshift using this. So, what we have is that it is 1 by 1 plus z. So, the integral on the left hand side can be written in terms of this observable redshift as C the integral 1 from 1 by 1 plus z, the scale factor when the light was emitted, to the present value of the scale factor of dA by A square H A. This is equal to the conformal time that has elapsed, that is C eta observed minus eta emitted. So, if we know the present value of the conformal time, we can use this to determine the value of the conformal time when the light was emitted. Okay, this is straightforward. Now, we can use this expression to also determine, okay, let us not go into that. Now, we would like to determine the coordinate r corresponding to that galaxy. To do that, what we have to do is we have to equate it to this. Let us first, so this will depend, this integral over here will depend on the value of k. Let us first consider the situation where k is 0. I have already told you that in the situation where k is 0, I can absorb this L inside into the coordinate, okay, and I can write. So, in the situation where k is 0, I can absorb that length scale L into the coordinate, give it dimensions length, okay. Or if you wish, we can absorb it inside the coordinate r. So, what we have is r is equal to C 1 by 1 plus z to 1 dA a square h a, which is also equal to C eta observed minus eta emitted, the difference in the conformal times. Okay. So, in this particular cosmological model, which is spatially flat, k equal to 0, this calculating this r, the coordinate distance is simple, it is given by this expression. Okay. Let us take up one example, one concrete example before going ahead. So, the example that we shall take up is as follows. What I mean by an example is that the relation between the coordinate distance r and the redshift z depends on the functional form of the Hubble parameter as a function of the scale factor. Let us take a model where there is only matter, omega matter is 1. There is no curvature, no cosmological constant or radiation, etc. So, in this model, what is the form of H of A? So, this is something which you should remember. We are going to use this again and again. I had told you that this is very important. So, in this model H naught, this is equal to H naught. There is omega matter naught, which is 1, and then I have A to the power. How does the omega matter scale with the expansion of the universe? How does the density of matter scale with the expansion of the universe? A, the density into A cube is a constant. So, it goes as A minus 3. So, I have the square root of that. So, it is minus 3 by 2. Okay. So, what we are led to is R is equal to C 1 plus Z dA and C by H naught over here, right, this 1 by H naught comes over here, and here I already have A square and now I have A to the power minus 3 by 2. So, this gives me a factor of square root of A. Okay. And I can do this integral. If I do this integral, I will get 2 C by H naught into square root of A at these two limits. What is the square root? So, this will give me 1 minus the square root of 1 by 1 plus Z. Okay. I have just done this integral, nothing more, and put in the limiting values. The upper limit gives me this, the lower limit gives me this. So, now we have the relation between the redshift and the coordinate distance to the galaxy. Okay. The first thing that we should check is that for small redshift, we recover the usual Hubble's law. What is the Hubble's law? The redshift is proportional to the distance, right. So, for small scale factor value, for small redshifts, we should check we recover this, right. Here the coordinate distance is the physical distance r. So, for small in our local universe, we should check that this actually gives us the Hubble's law. Okay. So, that is easy to check for small z. For z much less than 1, square root of 1 plus z to the power minus half this is approximately equal to 1 minus half z, right. I do a Taylor series and I retain only the first term, other terms I drop. So, if I put this in this expression, the first term 1 cancels out, and what we have is r is equal to 2 h naught 2 c by h naught into 2 z into half z, right. That is what we get from here. So, finally, we are led to r is equal to c by h naught into z, and in the local universe we can interpret c by cz as the speed at which, that is a Doppler interpretation, redshift into c gives us the velocity with which the galaxy is moving away from us, v by h naught, right. That is Hubble's law. So, we have seen that at small redshift you recover Hubble's law. Now, let us see what happens at large redshift. So, this the Hubble's law predicts a linear relation between the distance and the redshift, right. This is Hubble's law. Now, what about this expression, which is the correct expression in this particular model where the universe has only matter, omega matter equal to 1, it is spatially flat. Now, here at small redshift we have, it matches with the Hubble's law of expansion, but at large redshift let us see what happens. At large redshift this factor tends to 0 as z goes to infinity. So, at large redshifts the coordinate distance saturates at the value 2 c by h naught. So, it flattens out instead of increasing linearly at large redshifts. So, the deviations start at a redshift of around 1, and then at large redshifts it flattens out to a value 2 c by h naught. Okay. So, in this relativistic picture, which is the correct one, consistent one, the coordinate distance, the coordinate distance to the galaxy does not increase linearly with redshift. As I go to higher and higher redshifts, the coordinate distance does not increase as much, and as the redshift tends to infinity, the coordinate distance reaches a maximum value of 2 c by h naught. What is the interpretation of this? What is the physical interpretation of this? The physical interpretation of this can be best understood in terms of this space-time diagram. So, this is an observer, we are an observer, let us say, sitting over here. Let me draw the space-time diagram again. In this spatially flat model, r is exactly equal to the comoving distance. So, I can just replace it with the comoving distance, and we are an observer sitting over here at eta naught. So, this is c eta naught, this is the Big Bang. And this is the backward light cone. A signal from this position cannot reach this observer within the finite age of the universe, because a signal from here will propagate at light signal will propagate at 45 degrees, it will not reach here by present. Okay. This is the present age of the universe, this is the Big Bang, that is the history of the universe. In the history of the universe, an observer sitting here can only see up to this comoving distance, not beyond. Okay. Now, at this comoving distance, at this Big Bang, the scale factor has a value 0, at here the scale factor has a value 1. So, a redshift of infinity essentially corresponds to this. light coming from the Big Bang, where the scale factor had value 0. Okay, larger redshift means further back, and that is the furthest back you can see. So, this 2c by h naught, it is what is called a horizon. Okay, the size of the horizon, particle horizon, so the furthest distance that light can travel here is c eta, right, that is the furthest distance light can travel. If it starts from 0, that is the furthest co-moving distance light can travel, and this has a value 2c by h naught in this particular cosmological model. This is the particle horizon. This is the furthest distance signal can propagate if it starts propagating at the Big Bang. Okay. Regions larger, co-moving distances, large scales larger than this are not causally connected. So, let me stop today's lecture over here. We shall continue on this topic in the next class.